No, it is. He put it in at the beginning.
He was talking about why we use a silver
clusters are the baby bear of fluorophores because they're just right between size and photostability.
I called him out on it a month ago before submission.
You mentioned it here when you presented. I don't know.
Oh,
right at the beginning.
Yeah.
If you had a
it was very subtle.
I don't know if I'm ready to do
bear
that.
or bear or whatever.
I think I just like the subtleness of it.
Source
Some people can't.
put a source on the bottom.
No, like, this is fun. You can really use images, so then it would be much clearer kind of connection between the baby story and whatever you're showing there. It's fun. Why not?
Then people will recognize you after years.
Oh, he's the baby bear guy. He's the one that got Goldilocks wrong.
We are ready for the last but not least.
Yep.
Oh. Okay, thank you everyone. And I'm gonna present actually about the silver cluster oxidation and the ligations dependency of that silver cluster on photophysical properties. So actually I prepared this talk in by very short notice, so it's not very long presentation. So first I just directly move on the motivations why oxidation and the ligation is important part. First one is actually Sam also discussed about that one is very structural dependency of the silver cluster. So because of that is very advantageous to use in biological application like sensing and other properties. And another thing is before synthesizing this one, it's important to know the oxidation properties because the oxidation state is very important for determining the photophysical properties of the cluster. Is the one result is showing that in the experimental result, they didn't report the size of the silver cluster, but they're showing that there's the cyclovoltammetric graph. So when the forward bias is showing that this oxidation this potential peak potential, but in the reverse bias it didn't show any potential. So they're saying that this kind of silver cluster have irreversibility on the reduction potentials, and this peak also determine the irreversibility of this cluster. So this is important to know this oxidation potential of all of these cluster. And another thing is showing that they synthesize the silver cluster by using very different types of single strand DNA, and dependence on the types of the single strand DNA. I mean, population of the cytosine, guanine, or other nucleotides is showing that it can produce the green emitting or blue to red emitting silver cluster. So ligation also important in this case. So that's why I'm just trying to figure out what's the importance and how photophysical property is changing with the oxidation and the ligation types. So in the first, I just saying that in my methodology, first optimization of the one, and I took the bare silver cluster reported in the literature, and then I put the like guanine or cytosines on the surface silver cluster, and then took that geometry as an input geometry, and then optimized this one. And by using DFT and by using TT-DFT, I also I calculate this all photophysical properties and everything. And in the first part, for the calculating the redox potential, this is my methodology for calculating the redox potential. In this cycle is showing that have a thermodynamic cycle to calculate the redox potential, and I showing the redox cycle because in theory, in chemistry, physical chemistry, usually people report the redox potential. So if charge first I calculate the delta SCF energy in the vacuums and as well as in the water medium, and then from the and also the frequency analysis of this one. From the frequency analysis, I got the entropy corrections, thermalization corrections on that one, and balancing of all of this one, I can calculate the Gibbs free energy for the reduction reaction in water medium, and from that finally I will get the standard redox potential by using the standard hydrogen potential like 428 volt one. This methodology I followed for the reduction potential calculations. So this is the result for I calculate the reaction potential so far up to 4 to silver 10 cluster, and I'm also calculating the larger cluster too, but I not present it here. In the first panel is this the cytosine ligated silver cluster, and in the bottom panel is just a bare silver cluster.
You want to show geometry?
Okay. I didn't include that one here because there are a lot of geometry. I didn't determine which one should I show then. Yeah.
Just for illustration.
The beautiful,
Sorry,
the most beautiful one.
Yeah, since I need to add a lot of things here, it's just a very raw draft presentation of it. So in the first one is a dotted line, and the solid line is just is kind of the same types of reduction potential, but only solid line is showing the reduction potential of even number of silver cluster, even number size silver cluster, and dotted line is showing the odd numbers in silver cluster. So interesting thing is if we consider the very smaller size silver cluster like silver 4, and is showing that ON the reduction potential from the +1 to 0, it's showing that very high reduction potential in compared to the reducing from the +2 to 1 or 0 to -1. And if we're going to the even number size silver cluster is going to the opposite trend. In that case, ON is moving from the +1 to 0. It's showing the minimum reduction potential. That means actually is a spin multiplicity dependent, because +1 of the +4 is a doublet multiplicity, and neutral one is a single multiplicity, and odd number is in opposite trend. So that means ON is cluster is reducing from the doublet multiplicity to single multiplicity is showing the very high reduction potential. That means it's favorable to reduce this one. And in the other cases, in the odd number cases, is in the opposite way. ON is changing from +2 to +1 is a highest one. So that means spin reduction potential is higher. ON is changing the favorable multiplicity like spin multiplicity, and this all reduction potential is negative because is reduction potential. In other words, the oxidation is favorable. So if I compare with the experimental case which I showed in the motivations, is showing showing the agreement with experimental. That means his oxidation is favorable. Ultimately, you will get the positive charges of the cluster, and the oxidation state is determined by their spin multiplicity, especially in the lower cases. Now, when we are moving to the higher state, larger sizes from +4 to +10, and in overall in compare, but only one exception is blue one. I should show you here. This blue one, exception is this one. If
Blue is what?
This one is changing from the neutral to -1. It's supposed to be, we are expecting this higher reduction potential, but it's showing the very low reduction potential.
After size 10.
After size 10, yeah. Only size 10 here in this case. In other cases, the difference between these two different cases is going to decreases very smaller. And at the size 10, in the silver 9 is almost very close in this both cases. In the bare cluster also, they are almost
So
occupied.
top one's pacified. Okay.
Top one is specified and bottom one is bare silver cluster. So that means we are expecting that especially in the less than 10 sizes is very important their oxidation state to determine their based on their reduction potential. But when you're going to higher sizes, the effect of the spin is very going to diminish, reducing. And in this one, I just showing some from the electron affinity and ionization potential. It's also giving us a very same trend. One is going, and the odd number and even number is showing the same trend in compare if we compare with the reaction potential, which one is minimized and how is increasing with the going to the neutral to sorry no, even odd number to the even numbers. And now if we look on the absorption graph of this one, and in the doublet multiplicity, like 5 neutral and 5 1 minus is showing the very lowest very low energy peak on that one, but that low energy peak is going is diminished in the doublet in the single spin multiplicity. That means it has 5 1 plus and 5 2 pluses, and the intensity also increases. And the first one is the silver 5 and second one is the silver 6, and silver 6 also showing that same trend, but the lowest energy peak is going to be dark. And we also saw that when we going to the very large sizes and then low energy, this doublet trend is going to dark transition, that in the largest like silver 17 or silver 18 it didn't show this low energy transition.
Why is there so many lines? Like you have a neutral and plus 1, right? Or you have a...
No, there are 4 lines. I'm showing the neutral plus 1 minus 1 and plus 2 because I'm showing that how it's changing with the line. So oxidation potential is oxidation state is determining the shape of the absorption peak, how its intensity of the absorption peak too. So if we look on this one, in the same, in the doublet on first peak is high intensity in the silver 0 and 5 1 plus. So that means if we want to synthesize the smaller size silver cluster, we can determine the silver sizes by showing that from the absorption product, and their oxidation state also could be predictable from here. And in the next one, I'm just going to show about the ligation properties, how the cytosine. All of this calculation is done by passivation, by passivating the cytosine, because some experimental work showing that the cytosine passivated silver cluster also have a very strong illuminating luminescence properties. So in the next studies, I was trying to compare the ligands, how if we move from the cytosine to guanine ligands, how it's changing their trend. In this is a big table, so I'm just showing the same trend. In the first one, I calculate with the cytosine and with the guanine as well as the guanine and cytosine mixing. If this is comparing the bond energy, binding energy comparisons. If we look on this, this one is the plus neutral and plus 1, and neutral and plus 1 both in the silver 5 and 6. If we want, in the cytosine cases, if we are going to the doublet to the single, that means neutral to the plus 1 is increasing their binding energy, and the same in case of only guanine. But when this mixes with guanine and cytosines, the binding energy is following the opposite trend. And also this is true for the silver 6 cluster too. So from that, we thought that guanine is following the same trend if we follow the only guanines and only cytosine, but when they mix, it can following the opposite trends. One experimental work also showing that if we introduce a guanine-rich DNA in the cytosine-rich DNA, it can increase the photoluminescence by 500 times. So that means maybe it's important to know how to change the photophysical properties by using this one. So in this one, I calculate the absorption graphs for both 3 cases, for 5 and 6 for mix, and only guanine and cytosine is this one. It is almost giving the same absorption graphs, but the red one is showing that this is the mix cytosine and guanine ligand. If we look on the very closely, it is the second peak of this one. In the silver case, this is the silver 6 plus. There is also same multiplicity here. That's why I'm comparing with this one and this one. It is the second peak. these both cases, second peak intensity is increasing very significantly, especially in the silver 6 cases. So in the other side, it's almost presenting the same trend, but in this case, it's just overlapping with you. That's why it maybe increases a little bit higher. So in this case, we can say that if we add the guanine with the cytosine in the system, it increases, especially it's have a very effect in the second peak. I didn't show the NTUs here, but in NTUs it's showing that in the guanine mixture with cytosine, it's introduced the more cluster sphere from the silver cluster to the ligands. Because of that, I think it's influenced the intensity of this second peak in here. So this is the overall result from the cytosine and from this oxidation and the legal ligations. In the conclusions, I concluding that especially in the smaller size silver cluster is very important on the oxidation state. So we need to control the reduction environment. By controlling the reduction environment, we can control the photoluminescence properties of the system. And another one, this is also important, the types of the DNA strand. If we include the mix of the DNA strand, it can change the absorption properties, maybe as well as on the photoluminescence luminescence properties. I did not study the luminescence properties yet. By this, thank you all.
So, do you have questions? You do.
So when you're comparing the guanine and cytosine, why did you choose 4 and 2?
4 and 2.
So if you go back to that page,
5 and 6, not 4 and 2.
no. The number of each. So you have 3. No, go back to
You
the
mean
table.
P?
Here, you say,
And the mixed ligands.
oh, wait, yeah.
This one is the mixed ligand.
So you
Guanine,
have,
only cytosine participated in one.
so you say 3 cytosines and 2 guanine.
Because there are
Oh, yeah.
total 5
So
on
the
the 5
mixing of-
atoms.
So why did you not also consider the switch? So you say 3 cytosine and then 2 of the other. Why do you not do 2 and 3? Is there a scientific reason for that?
Not a scientific reason, but most of the studies is they saying the ratio of the cytosine is higher than guanine. Almost
So that
all
would
of the
be
studies, yeah.
Reason.
So in that case, I started more guanine than cytosine. Yeah. Sorry, more cytosine than guanine in the system.
More questions? So, I may have missed it, but for provided charge, sometimes there are different possible multiplicities. Like if like 2 plus, if there are 2 unpaired electrons, you can go to singlet and triplet. Or are you comparing each of those? Or you go into the sequence of different multiplicities and for given charge and seeing which of them are more stable? And did you
No, I didn't do that one. I just do the singlet one, and other cases didn't possible to single ones. Doublet is the minimum.
So you
I did
only
no.
singlet and double.
No, only
You
singlet.
never check
No, I
triplet,
didn't. No.
quadruplet or whatever.
No. I guess I started one
You cannot excite.
quadruple one.
Mhm.
You can't excite doublet. I mean, like for structure, 2 plus means even number of electrons, right? In your cases, are you talking because it's not so much 2 plus or plus 1. It's even numbers or odd numbers
odd
of
numbers.
electrons, right? You're talking about even number of
Yes, for
electrons
even one can
with a 2
construct
plus
the
charge.
So plus 4.
But you're still exciting singlet.
Are you presenting again on Friday?
Friday, no,
No,
Friday
will be
device.
easy. Device presentation probably will be too long for you to do it. But you feel like he needs more preparation from him?
I think, yeah, I need to add a little more.
Next week at ACS?
I prepared this one in just by 2 hours notice, so I will do the work on that more. I will add more
Who
data
knows,
here.
maybe you will not have a mood to prepare it further.
I have to. Yeah.
We have an option, right? You can practice it on probably Thursday,
I was
or you
thinking
can
to
practice
in
it.
Monday or
on
maybe Monday.
right?
Yeah.
Add structure.
However, for Monday, I probably will be busy since 8 o'clock till probably 4 p.m. because we have interviews for the director search for the entire day.
Maybe.
Oh.
Mm-hmm.
One comment
I mean, but you still can try with.
on your
other members.
figures. It's a lot of your slides. You talk about things in different figures, and you say if you compare this to this, and then this to that. Your figures, I don't think, are that representative of what you want them. It's kind of like taking spaghetti and throwing it against your fridge and seeing what sticks, and then trying to explain it. So it was very hard for me to follow your comments on your figures because
many
Mm-hmm.
you
lines.
jumped all over the place.
Yeah.
I agree.
Yeah, that's true because there have a lot of very huge number of data here. So suppose like this table, I didn't like this table even, but I didn't
Well,
get any.
But
This
I
table,
yeah.
by the way, not a problem, right? Because I think
No, I
this
mean
was
just for
pretty
example,
clear,
because
right? So you have binding energy larger here than here, but if you have a mixture, you have stronger binding, this with that. So this is pretty transparent data. I mean,
But
nothing wrong with the table,
Like-
but your absorption spectrum,
Yeah.
right? Very
Yeah.
confusing.
because like here you talk about
I would
Yeah,
say
I do not-
you probably need to eliminate some,
Polish.
not just polish, but just take out some lines. Let's
Yeah.
say, what's the reason to show 2+? Like, you can just mention that 2+ is a singlet which behaves very similar to your just plus singlet or zero singlet.
Mhm.
So I would say you probably can not consider this 2+ spectra
Yeah,
If it is-
or
if it
I
is
can
ru-
do
and
that.
just
Yeah.
show
really
+1
need them.
and neutral, like
Cri-
only 2
critically,
lines.
You may
for
make an
even and for
animation.
odd.
First, it appears
Yes.
one line.
Yeah, that's something.
Then
Yeah.
next, you click appears second line and make dashes and dots so that they are distinguishable. This red and magenta do not.
But again, because
Go.
if your lines, if the like going back to the comment from Levi, right? Looks like if your lines really very alike and they're not very much different qualitatively, right? And you just say, well, we clearly see a big difference between doublets and singlets, and whether it's +1 or +2 doesn't matter, right? You like this is your main point, right? Don't make your story more complicated. You can do this more complicated story when you will be